Buongiorno. Nuestro programa esta sera per el sujeto Rayos Cubicos. We are tonight on the subject of cube roots of the cubic equation. Okay, and Rayos Cubicos is a phrase which I got from a math book, and the rest I made it all up because, you know, those languages like Spanish and Italian and all that, they're quite unoriginal in thinking up, you know, totally original words for things like Chinese or Russian. The words are completely different, but, you know, Spanish, Italian, you can sort of pretend you're talking it. But Rayos Cubicos is a colorful way of seeing cube roots. And it comes from a story told by the late, great Richard Feynman in his book, Surely You're Joking, Mr. Feynman, about being down in South America one year teaching on sabbatical in a South American university, and being in a cafe when an abacus salesman comes in. And the abacus salesman was very proud of his ability to do complicated things on the abacus. And Richard Feynman kind of took him on in some rapid calculations, and first they were doing additions, and you see, this was in the 60s. This was before calculators, before the electronic calculators. Okay, so he was in a restaurant, and this abacus salesman come on, and he says he can do anything on the abacus. So he says, give me a column of figures. So the abacus salesman adds them up. Richard Feynman adds them up, and he's almost as fast as the abacus guy. So the abacus guy is sort of put out because you know, he's got to do better. So he says multiplicatio. So then they do some multiplications, and the abacus guy is sweating away, and Richard Feynman's doing the stuff in his head and just about beats him. Now the abacus guy is real pissed off, so he says Rayos Cubicos. So what he doesn't realize is that in math, when you're doing the things in your head, the more complicated things they get, they're not necessarily all that much more complicated to calculate. But to do them on the abacus by sliding beads, to take a cube root on the abacus, is an outrageous thing. So this time Feynman beats him, and then the guy picks up his abacus and leaves the store. Okay, that's my opening story. I don't think I did that great a job of telling that story, but there it is. Now I've taken up about 5 minutes from my valuable subject, which was the cubic equation. Okay, now taking a cube root of a number is something we can all do given enough time. Well, why am I telling you you can all do it? I can get a cube root of a number. But there's a much harder problem which bothered people, you know, hundreds of years ago, which was to unravel the roots of a cubic equation. And it's a very complicated thing. And I'm going to today show you how the methodology works when you try and take on a cubic equation. X cubed, take away 7x, take away 6 equals 0. And I picked this equation for a reason, because the solutions of it are very simple. I've generated this function intentionally to give simple answers by taking the simple terms x take away 3 times x plus 1 times x plus 2 equals 0, and I've multiplied these three terms together algebraically. If you know anything about algebra, you know that if you put 3 in here, it's going to null out this term and give you 0 in the end. Likewise, if you put -1 in here or -2 for x in any of these places, it's going to come to 0. So the three solutions for this equation have to be x equals 3, or x equals -1, or x equals -2. Now, you multiply them together and put it in this form. It's not so easy to see anymore, but you still got to have those three solutions for the equation. Okay.
And it's probably worth pointing out that although you can create an infinity of cubic equations by x plus a number times x minus a number and so on, that is really a small subset of all the possible cubic equations. In other words, there's cubic equations. The people who took grade 12 math 5 years ago want to understand, Marty, that you have equations with the solutions are not integers.
Look,
and they're
I've cooked
bizarre
them up.
numbers.
Yeah, I know.
Okay. I'm just trying to bring the point out.
So that the solutions will be easy. Okay, we'll see how easy they are, okay? We'll see how easy the solutions come out. Now I told you the solutions have to be easy. We'll see how easy they come out, okay? And I'll tell you later that what you say will be true, but you'll see how easy these come out.
Oh, I let out a secret too early. I'm sorry.
Okay, it's okay, Neil. It's okay. You haven't blown my cover yet.
Okay.
Now, what we have to do in looking for solutions of this, and people say that this is a pointless problem to work on. For reasons I talked about last week, I'm interested in knowing how this solves because I want to know how to solve even more complicated equations, the 4th degree equation and the 5th degree equation. When you get to the point where you put 5th powers of x up there, it turns out no one can solve them. I want to know why they can't be solved. And my approach is to look at how you solve the cubic equation. And you get a lot of fascinating insights into this question, which we're not going to have time to discuss in this mere 30 minutes of show after we've spent all this preamble just getting going on it. Okay. But my approach is to say, how did it look when we solved the quadratic equation? And we had x squared minus 7x minus 6 in there instead of x cubed. You did this in high school, and there was this formula, minus b plus or minus the square root of this and that. But when you look at all those things in the formula, really, the bottom line is you had a number, and you add to it the square root of another number, and that's what the solution looks like of a 2nd degree equation, the ones you solved in high school. There was b's and a's and this and that, but in the bottom line, it was a number plus the square root of a number. Notice a funny thing. Every number has 2 square roots because it's got a positive square root and a negative square root. Well, we sometimes put a plus and minus sign in there to show that when you write this formula, there's really 2 values that it takes on. And this is very suitable because you see there has to be 2 solutions for a 2nd degree equation. Now you've seen that when I wrote this formula here, there was 3 solutions that got to come up for this equation. So we need a formula like the 2nd degree formula, which has the ability to give us 3 solutions. Okay. Now there's one way you can do this that's easy, which is to put a cube root here instead of a square root. Because every number has 3 cube roots, okay? And then this would give you 3 solutions. But it turns out if you do this, it's not a powerful enough formula to solve this equation. You can't solve it with a simple formula like that. You've got to do something more complicated. Okay. So we'll go back to what we had for the 2nd degree and say, how can we make this more complicated? Okay? And I say, the simplest thing that you can do is to put some brackets around that and take a cube root of that, and then, a plus b to the 1/2 plus c, and then add something, maybe add another term to it. Okay. And this is maybe the simplest thing you can do that would still possibly have any hope in hell of giving you the solution. Okay. And the sad thing about this formula is that you got 2 square roots of a number, and then there's 3 cube roots of a number, and something terrible happens. When you look at all the values this formula can take on, there's 6 possible values that the formula can take on. And you got to have only 3 solutions. 6 values is too many. Okay, so what we do, and I'm going to tell you, I don't need this extra term here, because I've done something, I cheated. I didn't put a squared term in here. I have an x cubed term, an x term, I don't have an x squared term. I got rid of it just to make it simpler for TV. It's equivalent to that. I don't need a c term in this formula here. Okay, otherwise I'd need it. But I'm saying, I got this number, I'm going to call it p, and it takes on 2 values for choice of the square root of b and 3 different values for choice of the cube root. So I want to tell you I've got 6 different values, and I can list them in a table form by saying I could take the negative value for the square root, take the cube root and call that q, and then I'd have 3 values for p and q, which depend on different values of the square root. I'm going to call them omega times p and omega squared times p, and omega times q and omega squared times q, where the term omega represents the cube roots of unity. And you don't need to know what that means, but I'm telling you there's 6 values here that can come out of this formula. One formula gives you 6 values. Here they are listed in a table. Now the thing that people figured out, and this is like a miracle, is that anything you do to give you a formula makes it too complicated to solve the cubic equation. But they found a way to take these terms and group them and simplify them so that you get solutions out of them. And the way it goes is like this. It's almost unbelievable that it works. You take combinations, p and q together, Here's another combination, omega p plus omega squared q. And here's a third combination, omega squared p plus omega q. These three groups together form the three solutions of the cubic equation. I can't tell you why it is, but I can show you that it works, okay? I can show you that it works. I'm going to look for a solution of the form p plus q, where p and q are both of the form a plus b to the 1/2 to the 1/3. Okay, and I'm going to show you that they solve this equation. And we know the solutions have to be easy, so we'll see how they come out. I'm going to look for a solution of the form p plus q, and we'll see what comes out of it. Okay, take this off the board because I'm going to need a lot of room. What I write here is p plus q cubed equals, now we multiply this out as a polynomial using the rules of multiplying polynomials. I get p cubed plus q cubed, whoops, I'll do it in order, p cubed plus 3p squared cubed plus 3pq squared plus q cubed. Okay, now I'm going to regroup these things, okay? I have p plus q cubed, and what I want you to see is I can take this thing and factor out a term of 3pq out of it. I can factor out a 3pq equals 3pq times p plus q plus p cubed plus q cubed, okay? Now I've just written out the sum of p plus q in polynomial multiplication, and now a fantastic thing happens. I'm going to bring down the equation I started off with, x cubed minus 7x minus 6. I'm going to put the 7x minus 6 over to the right-hand side, like so. X cubed equals 7x plus 6. Now a fantastic thing happens. Do you see it, Sharon? Okay. I said p plus q was going to equal x, so there it is. P plus q is x. Here I said p plus q is going to be x, and there it is. P plus q cubed, I've got x cubed. What is left over? 6 has to be p cubed plus q cubed. 7 has to be 3p cubed. Okay, now that's my bottom line. This is what I got to. Now write those equations. 6 equals p cubed plus q cubed. And 7 equals 3p cubed. Okay. This is what I got to solve now. Now, I don't know if this is apparent to you, but when I got two things expressed as a sum and a product and got constant values for them, this is the equivalent problem to me having to solve a quadratic equation. And what I've done, which is a fantastic thing, is I started off with a third-degree equation, and what I got to solve now is only as complicated as a quadratic equation. We're going to see that this does solve. We're going to see that it does solve. And to help us solve it, we're going to remember what we said at the beginning, that the form that p and q take is that p equals a plus the square root of b to the 1/3, and q equals a take away square root of b to the 1/3. And then we're going to see that things like p cubed plus q cubed take on a very simple form. For example, p cubed equals a plus root b. Q cubed equals a minus the square root of b. So p cubed plus q cubed equals 2a. The b's cancel out. We got p cubed plus q cubed equals 2a. So I'm going to write that. P cubed plus q cubed equals 2a. So a equals 3. Okay. So now all I got to do is come back up here. Okay, take off some board space. And I had these p's and q's, and now I've got it down to the form. I'm looking for something 3 plus the square root of b to the 1 cubed is p, and I've got 3 minus, I've got p equals this, and q equals 3 minus the square root of b to the 1/3. And now I've got to isolate them further. I got to take advantage of this fact I got here in the bottom. P times q equals 7/3, okay? P times q equals 7/3, right there in the bottom of the board. If I multiply p times q together in this form, I get 9 take away b to the 1/3 is 7/3, okay? So p times q equals 9 take away b to the 1/3 power
Equals 7/3.
equals 7/3. Let's cube both sides. When I cube 7/3, I get 343 over 27. And I get to add b to the left-hand side, or take away 9 from this, so I get, let's switch things around. Okay, believe me, I've done this at home. b equals minus 1/100th over 27, because it comes out. Just tell you, b equals minus 1/100th over 27. You believe it, it's on TV. Okay, now I've got my p's and q's, and I'm going to write them out. I'm going to substitute the value for b in here, and I'm going to write it out the long way. P equals 3 plus square root of minus 100 over 27 to the 1/3, and Q equals 3 minus the square root of minus 100 over 27 to the 1/3. Okay.
You want the 27 in the root?
Yeah, okay,
Yeah, okay, okay,
let's
fine,
simplify it. You're right. I'm going to simplify it one more time. Simplify one more time. Okay. P equals 3 plus 10/9 the square root of negative 3, all to the cube root power. And Q equals 3 minus 10/9 the square root of minus 3, all to the 1/3 power, cube root. Okay, there it is. And P plus Q equals, and remember what P plus Q was? It was the solutions of that equation, and we knew what they were. It was either 3 or minus 1 or minus 2. Okay, I got them, the cube root of this and cube root of that. I defy you to identify that any of these numbers equals 3 or negative 1 or negative 2. Okay, this is how the mathematics comes out. I'm going to show you that we can evaluate these things, and it does work out to these numbers. This is almost unbelievable, but this is what I want to show you, if we have time. But first we got to do a song. Go to the piano. Any coffee left? No. Okay. That's okay. Just drop that cup off the side or something. Thanks, Sharon. Beautiful song. We've done it on the show before. It's a song by a Canadian singer called Joan Kennedy. It was on the country radio charts for a couple of months earlier this year. And unusual thing about this song is the chord motion is retrograde. For the first four bars of the song, the chord motion is going backwards. We go from a D to an A to an E to B minor 7. Okay, now, just to show you what I mean by retrograde, I'm going to tell you that if you reverse the order of that chord progression, you get something that sounds quite familiar. I'll show you that again. Here it is in the reverse order. That's forward motion of the chords.
Saturday in the Park.
Yeah, okay, a lot of songs use that sequence, okay. Saturday in the Park, good example. Okay, now, funny thing, retrograde chord motion, it makes the whole key tonality kind of ambiguous, so that you don't quite know hardly what key you're in at certain parts of the song. Gives a very unusual color, and Sharon does lead singing on this, and I put in a little harmonies. Neil's going to be noodling away on guitar, make it sound beautiful. Let's see how the whole thing sounds.
Walk me to the corner where the moon is full, saying never seen any moon as beautiful as me, never seen the stars shine so bright. I'm the one that you've been watching all night. Take me over where the lights are dim, give me something to remember, to forget about him. Do anything, darling, I won't fight, 'cause I never met a lie that I didn't like.
job was bring this back the next time
We
around.
could have, yeah, we should have
I
actually.
was thinking about it too. I
should've
figured
come
you
in.
might motion me to just do
No,
it
but
one
you see,
more time.
if we sing it one more time, we get
We're
the same
stuck.
problem again. You
It's
see,
a song that
because the
doesn't
reason,
really end.
the reason we went into that instrumental is because it doesn't really end on the chorus. So if we brought back the chorus, we know we're really
stuck.
better off than.
On the radio,
Whoa,
she
an
just
infinite
fades
loop.
again.
Whoa, yeah. Weird, eh? Okay, 5 minutes left in the show. That's nice. And just enough time to go back to the board and crank out these formulas. I said I had these unbelievable expressions, and I was going to show that they added up to. I had to take a cube root of something you can't even understand what it is. Okay, now I got to draw a graph to find what the heck numbers these look like. Okay. Here's how it goes. I don't know if you're going to like this. Oh, give myself a little room here. P's and Q's, they're conjugates of each other. We won't need to write them both down. What we got to draw is a complex plane. For those of you that don't know what the complex numbers are, well, I'm sorry. I'm really, truly, truly sorry, but I don't have time to explain them. It's a beautiful subject. But you got the square root of -1, so we got 1, 2, 3, -1, -2, -3.
Just give people a flavor. Tell them tell them the 3 cube roots of 1.
3i. No, that takes me all day, Neil. I've been through this
10
before.
seconds.
I've been through it before. I tried to explain the cube roots
you're
of
talking to a
-1.
dozen
Here
people
they
out
are. Here they are. There's the cube roots of -1. If I explain them, I'm going to use my last 5 minutes.
Okay, go, okay.
It's very important. They're located 120 degrees apart in the complex plane. It is important. Okay, now what I got to say, I have these numbers. I said were the key to solving this cubic equation. And I said it's 3 plus 10/9 the square root of -3. The square root of -3 is about so high, and this here is about 10/9 the square root of -3. This is the number I said I'm looking at. Okay. And I had P was this and Q was this. It was the same thing down below the reflected in the real plane. Okay, so there's my two values. I got to take the cube root of them. Okay, the length of this line is about 4 units long. If I take the cube root of 4, I come down about so far. Cube root of 4 is about 1.5 or something like that. Okay. Now I got to take the cube root of that, and that's the magnitude. And to take the cube root of the angle, you divide the angle by 3. So I divide the angle into 3 like so, and come down here in this direction. This is the cube root. Okay. I had this expression inside the brackets. Okay. So I plotted up to it, and then I said I had to take the cube root of it. So I took the cube root. That brings me down here. Okay. So here I am, and when I did the same thing with the complex conjugate, I had that one. Okay. Now what I'm telling you is when I add these two numbers together, they add like vectors. Bing, bang, bong, and there I am. 3.000. Okay. That's how I get 3 out of these numbers. Now I'm asking me, how am I going to get -1? How am I going to get -2? Okay, and here's how it works. Anytime you take a cube root, you get 3 values, and they're located on a circle 120 degrees apart in the complex plane. So I draw the circle in the complex plane. Circle in the complex plane looks like this. I take the cube root I had over here, and I locate position over here and over here, 120 degrees apart. 1, 2, 3. Okay, 120 degrees, 120 degrees, 120 degrees. Okay, that's my 3 cube roots of P, and my yellow ones, which is the conjugate values, the cube roots of -P, are just located over here and over here. Okay, Neil, you're going to make a point here?
No, 1 minute left.
1 minute left. Okay, and here's how it goes. You add together this pink one and this yellow one, projects down to here to -2. Okay, that's -2. I add together these two and I project down 1, 2 here, project to -1. There's my 3 solutions. 3, -1, and -2. Okay. You like it?
Very nice, Marty.
It's unbelievable. I mean, an expression like that, how are you ever going to come up with a nice number out of it? But you think, what it means, I think, is this is the simplest mathematical expression under which the 3 numbers, 2, 1, and -3, share the same arithmetic properties. Strange thing. And what it leads to, you know, is almost unbelievable. But we're out of time. But let's just take it out with a little bit of music. And, Gore, you know what we do? We just keep playing the song until, and then you overlay that math with Marty Freeze over our song as we play out. Love, there's only you in my life, the only thing that's right. that